Late in the afternoon on July 24th, 2026, engineers at Starbase in South Texas watched a rocket the size of a skyscraper rumble off the pad for the 13th time. Nobody there was superstitious about the number, but everybody understood the pressure riding on this particular launch. Now, the last few months hadn't been kind to the Starship program, and this flight needed to prove the newest version of the vehicle could actually do what it was built to do. What unfolded over the next hour turned into one of the more genuinely pivotal moments in the whole Starship story. Part triumph, part cautionary tale, and entirely unlike any test flight that had come before it. Context matters here. This was only the second time SpaceX had flown its overhauled Block 3 version of Starship, a rebuilt vehicle designed from the ground up to eventually haul far more cargo and fly with far greater consistency than the earlier iterations. The debut of this new hardware, back in May, hadn't gone smoothly. The booster came down off target during landing, and the ship itself lost an engine early into its climb, cutting the mission short of most of its intended objectives. So going into Flight 13, the real question wasn't just whether the rocket would fly. It was whether the redesigned Block 3 architecture could finally deliver a clean, complete demonstration. Just getting the vehicle into the sky proved to be a battle on its own. The first launch attempt, on July 16th, never made it off the pad. As the Super Heavy boosters 33 Raptor engines began spinning up for liftoff, onboard software caught something wrong and slammed the brakes on the countdown at the very last instant, a split-second automated call that kept both the rocket and the launch tower from potential disaster. Engineers dug in and found the culprit. Oxidizer turbopumps in several engines, somewhere between 4 and 6 of them, had picked up trace moisture that froze solid on contact with the deep chill of the cryogenic propellant, throwing off how fast those pumps were meant to spin. Rather than gamble on flying with compromised hardware, the system did its job and shut everything down before ignition ever finished. Over the following week, SpaceX swapped out the problem engines. In a nice bit of extra caution, one of the pulled Raptors was flown to the company's McGregor, Texas test site and put through a complete ascent-length burn on a stand, just to confirm the fix actually solved what had gone wrong before trusting new hardware back on the rocket. A second launch. Attempt was scheduled for July 23rd, but that one got scrubbed too, this time simply because the weather refused to cooperate over the coastal launch site. Finally, on the evening of July 24th, under clear Texas skies, Starship got its window. After a short built-in hold, the countdown resumed and the rocket lifted off cleanly. This time, all 33 engines on the Super Heavy booster ignited exactly as planned, a feat that's genuinely difficult to pull off given how many separate engines have to fire up, throttle correctly, and stay in sync on a vehicle this large. At roughly 408 feet tall, taller than most buildings in any American downtown, the fully assembled Starship thundered skyward into a mostly cloudless afternoon. The climb followed SpaceX's now standard hot staging approach, where the ship's own engines ignite while it's still bolted to the booster, using their thrust to physically shove the two halves apart instead of relying on a slower mechanical separation. That handoff went cleanly. The booster then flipped itself around and fired a portion of its engines in what's called a boost backburn, canceling its forward momentum to steer itself toward a landing zone, while the ship's 6 engines kept burning to push it onward. From here, the flight essentially became 2 separate stories, one for each half of the vehicle, and they ended very differently. The booster's story is where things got rocky. Super Heavy wasn't headed back to the launch site this time. It was always meant to come down in a controlled but disposable splashdown out in the Gulf of Mexico. As it neared the water, it attempted to relight 13 engines to slow its final descent. Only 10 of those actually caught, and 5 of those 10 cut out again just seconds later, leaving the booster with considerably less braking power than intended right as it approached the surface. It hit the water harder and faster than SpaceX had hoped for. The touchdown was still broadly under control, and since SpaceX never planned to recover this specific booster anyway, the rough landing didn't sink the mission so much as flag an unresolved problem. One more instance of the tricky, high-stakes engine-relight challenge that still needs solving before booster performance becomes fully predictable. The ship, meanwhile, turned in what was close to a perfect flight. Once it reached space along its deliberately suborbital path, Starship's upper stage carried out one of the most ambitious payload demonstrations any Starship flight has attempted so far. On board were 20 next-generation Starlink V3 satellites, and unlike the 6 previous test flights, which had only ever carried dummy, mass simulators shaped like satellites but incapable of functioning, these were the real thing. Once released, they unfolded their solar arrays and antennas and made a brief attempt to link into SpaceX's existing Starlink network using intersatellite laser links, actually testing operational readiness rather than just proving the deployment hardware worked. Because this particular flight path was intentionally suborbital, none of the satellites were meant to stick around. All 20 burned up, re-entering the atmosphere roughly 20 minutes after being let go. 6 of those 20 carried something extra. purpose-built camera rigs bolted on specifically to photograph Starship as they drifted away. SpaceX described the maneuver as its own version of the rendezvous pitch maneuver NASA once relied on with the Space Shuttle, where the orbiter would flip over near the space station so astronauts could photograph its underside heat shield tiles for signs of damage before re-entry. Having a swarm of departing satellites document the condition of Starship's heat shield and engine section from multiple angles gave engineers a completely new stream of external imagery captured in real time well before that same heat shield would face the far more brutal test of atmospheric re-entry. The ship also pulled off an in-space engine-relight, successfully reigniting one of its Raptor engines while coasting through the vacuum of space, a smaller milestone on paper, but an important one, since dependable relights in orbit are essential groundwork for any future mission involving precise deorbit burns, trajectory changes, or eventual propellant transfer between vehicles. Then came the moment that genuinely caught people off guard, including plenty of engineers watching inside SpaceX itself. As the ship dropped back through the atmosphere on its way toward a splashdown zone in the Indian Ocean off Western Australia, it survived the heat of re-entry and pulled off Starship's now familiar landing flip, rotating itself from a horizontal belly-down orientation into a vertical position in the final seconds before touchdown. It splashed into the ocean, and rather than breaking apart on impact the way earlier prototypes had during similar water landings, the ship touched down more gently than any Starship before it. SpaceX's own launch commentary team called it the softest ocean landing the vehicle had ever pulled off. The ship did eventually roll onto its side once it settled in the water, something engineers had expected given the vehicle was never designed to stay upright indefinitely on the open ocean, but critically, it stayed in one piece. It didn't explode or come apart the way several earlier Starship prototypes had during past re-entry and landing attempts. Instead, it floated belly up, fully intact, and kept beaming telemetry back to mission control even after splashdown, a first for the program, since no previous Starship had survived an ocean landing well enough afterward to keep functioning and communicating from the water. That survival opened up something SpaceX had never really gotten to do before, inspect a splashdown Starship up close while it was still whole. A drone flew out to the floating vehicle and captured detailed footage of it rocking gently in the waves, including views of a small fire that had broken out near the nose section during or shortly after landing. Despite that fire, the ship stayed afloat and mostly intact through the inspection, handing SpaceX real physical imagery of what the vehicle's heat shield and structure actually looked like after a complete flight, instead of relying purely on remote sensor data the way nearly every earlier test had required. Elon Musk later said SpaceX intends to actually recover this Starship from the ocean rather than let it sink, which, if it happens, would give engineers a rare chance to physically examine a flown vehicle's heat shield tiles, airframe, and engines back on solid ground rather than through imagery and telemetry alone. Put together, SpaceX described Flight 13 as a fully successful end-to-end test of the ship, running from stage separation all the way through splashdown, and said it checked off the verification, steps needed before the company attempts an actual orbital Starship mission. The booster's rougher landing got filed away as a known problem to fix, rather than a serious setback, especially given that SpaceX had never intended to reuse this particular booster in the first place. It's worth pausing to appreciate just how unconventional this whole style of rocket development still is. Most rockets throughout aerospace history get designed on paper, run through extensive simulation, and only fly once engineers feel reasonably confident the vehicle will behave, treating any failure as a rare and expensive embarrassment. SpaceX has built Starship almost the opposite way, flying full-scale, functional prototypes again and again, deliberately pushing them until something breaks, then rebuilding, and flying again within months instead of years. From the outside, especially during Starship's earliest flights, several of which ended in fireballs visible for miles around Starbase, this looked almost reckless. But it's the exact same iterative approach that eventually let SpaceX perfect Falcon 9's booster landings, turning something that once seemed borderline impossible into a routine, repeated operation. Flight 13 is simply the newest entry in that same long, expensive, occasionally explosive learning process, except this time the outcome tipped more toward success than failure, particularly on the ship's side of things. The Starlink deployment on this flight deserves its own spotlight because it hints at the real commercial logic driving much of Starship's development. SpaceX's existing Falcon 9 rocket already handles the overwhelming majority of Starlink launches today, but Starship is built to carry dramatically more mass and volume per flight, meaning a single Starship launch could eventually deliver as many satellites as several Falcon 9 missions combined. Successfully releasing 20 functioning next-generation Starlink V3 satellites on Flight 13, and watching them attempt genuine laser communication links with the existing constellation, was a meaningful sign that Starship is edging closer to becoming an actual working satellite delivery system, rather than staying purely an experimental test vehicle. The fact that these satellites briefly operated for real, even on a suborbital flight destined to end in atmospheric burnup minutes later, sets Flight 13 apart from every prior mission that only carried inert stand-ins. The booster's harder splashdown, on the other hand, fits into a pattern SpaceX has been wrestling with since this newer Block 3 hardware entered testing. A related category of problem, engines struggling to relight reliably during the critical landing burn, had already shown up in a different form on the Block 3 debut. Flight back in May, when the booster missed its splashdown target entirely. Seeing a similar issue resurface on Flight 13, even in a smaller, more contained way, suggests SpaceX is still working through teething problems specific to this redesigned booster's engine and propellant systems, separate from the issues that plagued the earliest generations of Starship years earlier. Engineers will now comb through the flight data to figure out exactly why 5 of the 10 relit engines cut out again so quickly, the same way they traced the earlier pad abort back to frozen moisture inside the oxidizer turbopumps. Not long after Flight 13 wrapped up, Musk announced that the next mission, Flight 14, is aiming to go even further, with SpaceX planning to attempt catching the ship itself using the giant mechanical arms mounted on its launch tower, nicknamed Mechazilla. That catch technique has previously only been used on the super heavy booster, never on the ship, and pulling it off would require Starship to actually reach orbit first rather than fly the intentionally suborbital hops it's flown so far, a substantial jump in ambition. Even before Flight 13 launched, SpaceX President Gwynne Shotwell had said that if the mission went well, the company hoped to attempt its first fully orbital Starship flight on Flight 14, to be followed by Flight 15, which would mark Starship's first ever launch from a pad in Florida rather than Texas, opening up an entirely second launch site for the program. There's also a bigger picture worth keeping in mind here, one that goes beyond any single flight's tally of wins and losses. Starship isn't just a larger successor to Falcon 9, it's the vehicle NASA has selected to land astronauts back on the lunar surface under the Artemis program, and it sits at the center of Elon Musk's long-running ambitions for eventual crewed missions to Mars. Every relight failure, every hard splashdown, and every successful satellite deployment feeds directly into whether that far more ambitious timeline stays realistic. A booster that can't reliably relight its engines during a landing burn over open water becomes a much bigger concern once that same booster is expected to one day bring astronauts home safely, rather than simply splash down and get discarded. That's a big part of why SpaceX pores over even a mostly successful test, like Flight 13 in such detail, sifting through telemetry from tens of thousands of sensors, because the margin for error keeps shrinking as actual crews get closer to being involved. It's also worth remembering just how quickly this whole program has been moving. 13 full integrated test flights of a vehicle this large and complex in only a handful of years is an extraordinarily fast pace by the traditional standards of the rocket industry, where a brand new vehicle design has historically taken most of a decade just to reach its first launch. SpaceX's willingness to fly early, fail often, and iterate quickly, sometimes to the visible frustration of onlookers watching rockets explode on live streams, is exactly what has let the company rack up 13 flights of a vehicle this ambitious in such a short window. Flight 13's mostly successful outcome sits right in between the dramatic early explosions of Starship's first prototypes and the fully routine, catch-equipped orbital missions SpaceX is now chasing, capturing the program at that awkward, promising middle stage where real breakthroughs and lingering hardware issues keep showing up on the very same flight. It's also worth zooming out on the sheer scale of what's involved in a single Starship launch, because the numbers are almost hard to process. The combined vehicle, booster, and ship stacked together stands taller than the Statue of Liberty, including its pedestal, and burns through more thrust at liftoff than any rocket ever flown, roughly double what the Saturn V produced at the height of the Apollo program. Fueling that stack requires millions of pounds of cryogenic methane and liquid oxygen, chilled to hundreds of degrees below zero, and pumped through the vehicle in the hours before launch. Every one of the 33 engines on the booster alone has to be individually monitored, throttled, and, if necessary, shut down in milliseconds if something goes wrong, all while the vehicle is accelerating through the thickest part of the atmosphere. Against that backdrop, getting all 33 engines to ignite cleanly on Flight 13, something that has not always happened on earlier missions, was itself a meaningful achievement, even before accounting for everything that happened afterward. There's also the human side of a mission like this, easy to lose, in a recap full of turbopumps and telemetry. Inside SpaceX's mission control, engineers who had spent the better part of a year designing, testing, and troubleshooting Block 3 hardware watched their work either succeed or fail in real time, compressed into roughly an hour of flight, the two-scrubbed launch. Attempts alone meant weeks of additional waiting, rechecking hardware and second-guessing fixes before the rocket ever got another shot at flying. When the ship finally splashed down intact in the Indian Ocean, still transmitting data instead of going silent in an explosion, the reaction from SpaceX's live commentary team was audible relief as much as excitement, a sign of just how much uncertainty still surrounds every single one of these test flights, even after 12 previous attempts. So where does that leave things? Despite 2 scrubbed launch attempts and a booster that splashed down harder than planned, Starship's 13th flight delivered real, functioning satellites into space for the first time, relit an engine in orbit, survived a complete reentry, and then, almost unexpectedly, gave the world its first look at an intact Starship floating calmly in the ocean, instead of vanishing in a fireball. Lucky number 13, as it turned out, mostly earned its nickname.